Okay, so let us recall what we were doing. In fact, what the last point was. We considered a field f, any field, and we considered a polynomial f over f, fx over f, or a polynomial fx in this polynomial ring fx. We have managed to prove already that this polynomial has a splitting field E. What that means is that E is an extension of f satisfying these two properties. When you consider the polynomial as an element in this larger polynomial ring Ex, which you can do because you have this containment, f is a subfield of E, so naturally fx is a subring of this other ring, polynomial ring Ex. So you can consider this element also as an element of Ex. Now when you do that, fx suffers a total decomposition, or in other words has a factorization of this form. That is, fx can be factored as a product of linear factors, degree 1 polynomials. This c of course will be there to adjust the leading coefficient of the polynomial, our original polynomial fx, which may not be 1. But factoring fx in Ex in this form simply means that this c and this ai's are coming from this extension E and not necessarily coming from this original field f. So that is the first condition, and the second condition is that E is minimal. That is, we are not in an attempt to cause this decomposition just like a madman considering an extension E of f as large as we can possibly consider, so that this is bound to happen. No, we are not putting unnecessary, we are not adjoining unnecessary elements to f to have this extension E. We are just considering an extension E that is just the right amount of extension to cause this and nothing more. More precisely, what that means is that the degree of E over f is minimal. That is, when you consider E as a vector space over f, this dimension is minimal. Okay, so that means every polynomial over any field has a corresponding splitting field E. Fine, so existence of splitting fields have already been proved. Now, the next thing to consider naturally is this. Fine, so if every polynomial has a splitting field, it may have more than one. So we can have two splitting fields E1 and E2 of the same polynomial fx. So the next natural question to ask is, what is these things have any relationship between them? And if so, what is the relationship? We have already stated it in the previous video. So let's just write that down again. There is an isomorphism T of, I cannot remember what we called this one, or even if we called anything, I mean this isomorphism, we called this by any name or not, but here let's just call it T. There is an isomorphism T of E1 onto E2 such that alpha t is equal to alpha for all alpha belonging to F. Keep in mind that being a splitting field, for example, E1 is a splitting field of Fx, which is a polynomial coming from this polynomial ring. So E1 is by definition an extension of F, that means F is sitting inside E1. So T can be restricted to this subset F. Now if you do that, then T becomes the identity map on F. That is, T does not affect F at all. It fixes the entirety of F. Now we want to prove this very nice looking result. That is our next goal in this section, which however cannot be proved at once. We will have to go through 2 or 3 results, and then only we will gather the necessary tools using which we can prove this. So it's towards that direction we are now heading. So you can see that because isomorphic fields are involved, so the discussion will now naturally start with isomorphic fields. So this is how next Herstein proceeds. Let F and F prime be two fields, and let tau be an isomorphism of F onto F prime. Okay, so the fact that F and F prime are isomorphic is in fact that isomorphism is given by this isomorphism tau. Note one more thing, that in this discussion that we are now writing down here from the next paragraph, here F and F prime, at this stage we are not saying anything about splitting fields or extensions, anything. Just simply we have considered two fields which are isomorphic to each other, and tau is an isomorphism between them. It is. So now let us simplify our notation a little bit. It is convenient to write the image of alpha in F under tau as alpha prime. That is, alpha prime is the image of alpha under tau. Since we will be considering images of the elements in F under tau a lot, so naturally it's a little cumbersome to again and again keep writing this tau, alpha tau, beta tau, and so on. So instead this notation is much less time consuming. We shall maintain this notation for the next few pages. Okay, because since I am writing everything down, so let me just write this also. We are going to maintain this prime notation for the next few pages. Of course I cannot write because I don't have pages here, but we will write something else in what follows, for example. Or maintain this notation in the rest of this section. Now next the author asks this question. Now the situation is this, right? Tau is an isomorphism of the field F onto F prime. Now can we use this tau to set up an isomorphism, say tau star, between these polynomial rings? That is our next question, and in fact we can do that in a pretty straightforward manner. So let's see what that isomorphism is. Why suddenly we are going again to polynomial rings? We will see. Let's just first answer that. Now define tau star from fx into f prime t as follows. To keep things as distinct as possible, we are denoting the indeterminates in these two polynomial rings separately using separate symbols. This one we are calling x and this one we are calling t. Say for fx, so fx is now going to be an element here, so it's a polynomial, say it's this polynomial. Belonging to fx, we define fx tau star, the image of fx under tau star, to be equal to this polynomial. Now does it make sense? What we have done is that we have taken a polynomial in this first polynomial ring, then we have replaced that with a similar looking polynomial but in this polynomial ring. So the coefficients of this image should come from f prime. But we already have a relationship between f and f prime given by tau. So we have used that tau here in writing these new coefficients. The new coefficients are just the tau images or the images of the old coefficient under tau. That's just it. Because this alpha naught prime, for example, is the image of alpha naught under tau. Okay, so now the first thing next we have to see is that this function tau star is a well-defined function. If we don't have a well-defined function, then we can, of course cannot go any further and the story stops here itself. Well-definedness demands that if we take any element here, for example we have taken this fx, then this image must first of all be here in f prime t, and the second thing is that it should be unique. So are we having that? The fact that this image is in f prime t is understandable because this alpha I primes are in fact in, all of them are in this field f prime. Okay. Now what about uniqueness? Do we really have uniqueness? If you think of it, say you have another expression for this fx like this. where the beta i's or beta j's are also coming from F. Then equality of two elements in this polynomial ring Fx tells us that m must be equal to n and each alpha I must be equal to beta I. In other words, this expression expressing the polynomial Fx is itself unique. In other words, still, what this simply means is that these alpha i's are uniquely determined by Fx. So you have these alpha i's and you won't have any other set of coefficients. So because the alpha i's are unique, their images under tau are also unique. The alpha I primes are unique elements in this second field F prime, and that is why this polynomial in F prime t is a unique element in F prime t, and that is why our function tau star is well defined. In fact, you have to write these things down ideally, but I have just simply given you the explanation, and I am not going to write things down in any more detail than this. I will just simply mention clearly this is well defined. Okay, now the next thing to prove is that this tau star is a ring homomorphism. So for that we need to consider two elements. One, of course, we have here Fx, another one we will consider Gx. So let us consider in fact let us take Gx like that, b beta naught plus beta 1x etc. plus beta mx to the power n, because in general n and m may not be the same, they need not be the same, and they won't be the same if you consider Fx and Gx like that. Say n is 2 and m is 3, that can happen. And that is why now, since we are going to add Fx and Gx, so let us adjust things in such a way that they do have same expression. Same expression means at least these n and m are same. They are not same, but we are now forcefully going to make them same by introducing zero terms, zero coefficients wherever necessary. Precisely that means this. Assume without loss of generality that say n is greater than or equal to m, then we can write, because n is greater than or equal to m, so we can now write this Gx in a different form. Gamma naught plus gamma 1 x etc. plus gamma n x to the power n, where gamma I is defined to be equal to beta I if I lies between, I varies from 0 to m, and gamma I is defined to be equal to 0 if I varies from m plus 1 to n. If n actually happens to be equal to m, then this part is not there. It just simply means that. Now, okay, let us now start our calculation. We calculate the sum fx plus gx, and on that we are going to apply tau star. Now, because fx is already a polynomial looking like this, and gx now also looks like fx in this new representation, so it becomes easy to add them up. Doing so, we get alpha naught plus gamma naught plus alpha 1 plus gamma 1 x plus, without cluttering the space, let's continue from here. We can remember what tau star is or what its definition is. Replace every coefficient by its image under that original function tau. Plus alpha n, yes, plus gamma n x to the power n. On this we are applying tau star. Now, for the sake of clarity, let us for once not just use this prime notation and see what this thing is going to be in detail. That is, if we apply tau star on this polynomial, then we are now going to get alpha naught plus gamma naught tau, the tau image of this, plus the tau image of this t. The t is there because keep in your mind that we are now writing a polynomial in this polynomial ring, f prime t, so powers of t and all those things will be there. Plus alpha n plus gamma n tau t to the power n. Now, because tau originally is a homomorphism, it's in fact an isomorphism from f onto f prime, and these are elements from f. So tau will respect addition, so this will be equal to the first term alpha naught tau plus gamma naught tau. Like that, the second term will be alpha 1 tau plus gamma 1 tau t, and it will continue like this. The last one will be alpha n tau plus gamma n tau t to the power n. Now, by the definition of addition in the second polynomial ring f prime t, this can be written as alpha naught tau plus alpha 1 tau t plus alpha n tau t to the power n plus gamma naught tau plus gamma 1 tau t etc. plus gamma n tau t to the power n. and this will be equal to, we can instantly recognize the first one. It is nothing but alpha naught prime plus alpha 1 prime t plus alpha n prime t to the power n. And in the second one, you can use the fact that these gammas in fact have been conveniently, they are just simply the betas, but maybe some possible zero terms are there. T to the power m plus these possible extra terms are there, gamma m plus 1 tau gamma n tau t to the power n. What is this first one? This first one is nothing but the tau star image of f of x, and in this second term, the first part is now when I varies from 0 to m, gamma I is just simply beta I. Plus, and all these higher gammas, if they exist, are 0. Now these terms, all of them will become 0, but do you see exactly why? It is because tau is a homomorphism, a ring homomorphism, so it will map the 0 element onto the 0 element, and that is why all these are zeros. The zeros that we have written here, that means you have 0 tau here, in the next one also you have 0 tau, this last one is 0 tau. In all these terms, the 0 is the 0 of the first field f. And this 0 tau, these things that you see here in this last a number of terms, they are, all of them are the 0 element in the second field f prime. Okay, keep that is a distinct thing. F and f prime may be isomorphic fields, but they may be entirely different things. I mean, the objects in f may be a type of object, the objects in f prime may be a completely different type of object. So that means ultimately these terms, they will just simply vanish, they do not survive. Plus, now you can use our slightly less cumbersome notation and write this like this. Now this second term is nothing but the tau star image of the second polynomial gx. So we started by considering the term fx plus, considering the sum fx plus gx, and in fact we were applying tau star on that sum. So it turns out to be equal to this. So tau star respects addition. We have shown that thing. Now next we want to show that tau star respects multiplication. For multiplication, however, we don't need these gamma i's. We can just simply work with the original fx and original gx. So next we want to first of all calculate this product, and then on the product we want to apply tau star. So we have to be rather careful. And in fact, let me just write down what is it that we had. Fx is this polynomial alpha n x to the power n, and gx is this other one, mx to the power m. So that means if we take the product of these two polynomials, we will get this polynomial alpha I beta j I plus j equal to k. If you want, you can write this inner sum in a slightly different manner without using two variables I and j. Say you write, because I plus j is k, so instead of writing j, you can write k minus I also, but I choose to write like this. For some reason, this is easier for me. K equal to 0 to n plus m, and here you have x to the power k. On this product we are going to apply tau star. Now this clearly is itself in a polynomial in the standard form. These are the coefficients and these are the monomials x to the power k, and this itself is that sum expression. So we can directly write what the tau star image of this polynomial is. It's going to be the outer sum, which is the polynomial expression, that just is going to be the same thing because of the definition of our tau star. In this inner sum, which is in fact the kth coefficient, on that inner sum we are going to apply our old function tau, and because now the polynomial is going to be a polynomial in the indeterminate t to the power k. Okay. Now use the fact that tau is an isomorphism from the field f to the field f prime. In fact, we just simply need the fact here that tau is a homomorphism, ring homomorphism. So tau will respect both addition as well as multiplication. So that means we can take tau inside of this sum, and not just inside of this sum, inside of this products also. What that means is just simply this: alpha I tau beta j tau equal to k t to the power k. If you feel somewhat uncomfortable writing this at once, you can do it in two steps. First, you apply tau to all the terms of this sum for a fixed k. That means in the next step you would write summation I plus j equal to k tau image of alpha I beta j, and then you write this one. all these calculations look complicated, but as you can clearly see, it's absolutely straightforward. There is no trickery involved. Everything is as natural as things can be. N plus m. So now we can use our simple notation. In place of alpha I tau, we can write alpha I prime, beta j prime, where I plus j is equal to k, t to the power k. And this you can clearly see is the product of these two polynomials, alpha naught prime plus alpha 1 prime t, etc., plus alpha n prime t to the power n times beta naught prime plus beta 1 prime t, etc., beta m prime t to the power m. The first factor is the tau star image of fx, and the second factor is the tau star image of gx. Okay, so we have shown that tau star respects not only addition but multiplication also. Hence, is a homomorphism. Since we are dealing with fields and rings, so it's understood we are talking about ring homomorphism. But I repeat what I said previously also many times, that if more than one type of algebraic structures are involved, say you have groups as well as fields, you will see one such situation will arise in Galois theory. Then we need to mention group homomorphism, ring homomorphism explicitly. So this is a homomorphism. Now only thing we next need to show is that this is one-to-one and as well as onto. Next, let fx be in the kernel of tau star. If we can prove that this implies fx has to be the zero polynomial, then the kernel has only the zero element, and hence the function tau star will be one-to-one. Or if you want, you can show one-to-oneness directly also. There is a mistake that is often committed by people, is that people tend to forget that the word kernel, it is of a homomorphism. Now before you show that a certain function is a homomorphism, you cannot use the kernel criterion to show that the function is one-to-one. So now that we have shown that it's a homomorphism, now it makes sense to say things like this. Tau star. Then alpha 1 prime t plus alpha n prime t to the power n, which is the tau star image of fx, is 0, and you can clearly see that this 0 in this context is the zero polynomial in this second polynomial ring. So by the definition of equality in this polynomial ring, this polynomial is 0 if and only if its coefficients are 0. So which implies shall I write at once, or let me just write it in detail as a number of equations. Alpha naught tau, which is alpha naught prime, that is equal to 0. Alpha 1 tau, which is alpha 1 prime, that is also equal to 0, like that. Alpha n tau, which is alpha n prime, that is also equal to 0. Okay. Now tau itself, our original tau is an isomorphism, so that is 1 to 1, since tau is 1 to 1. We have alpha naught, alpha 1, all the alphas are now going to be 0, i.e. fx is 0, because all its coefficients are 0. If our fx is that original fx, okay, where we started our calculation, and in fact where we what we used in order to define tau star, that fx, this is equal to 0. This shows that tau star is 1 to 1. Next, the only thing left to show is that tau star is onto. So for that we will have to consider any polynomial in this second polynomial ring and prove that it equals the tau star image of some polynomial in the first polynomial ring. Next, consider any polynomial. I think I need ink. Consider any polynomial, say h. Keep in mind we are now going to consider a polynomial in the second ring, so our indeterminate should be t. Say this is delta, we are starting with 0, right? Delta 1 t, etc. Say delta s, t to the power s, in f prime t, since tau from f to f prime is onto there exists nu naught, nu 1, etc. nu s belonging to f such that delta naught is nu naught tau, delta 1 is nu 1 tau, and delta n is nu n tau. Then h of t I took s and here again I am writing n. T to the power s, this is nu naught tau plus nu 1 tau t t to the power s. Now using our simplified notation, which really we are not using that much because we are in fact writing everything, but we are writing this thing for the sake of understanding so that we don't get confused. Prime t to the power s, and this by our definition of tau star is this. Where clearly the polynomial of which we are finding the tau star image here and which turns out to be equal to h of t, clearly that polynomial is in the first polynomial ring therefore tau star is onto. Okay, so now we have completely shown that the function tau star we defined a few moments back is in fact an isomorphism of the first polynomial ring onto the second polynomial ring. So our whatever we have done here, we can write that down in the form of a lemma. This is lemma 533. Referring to, of course, what tau star actually is, we directly write like this. Tau star defines an isomorphism of fx onto f prime t, but there is something else also, with the property that alpha tau star is equal to alpha prime for every alpha belonging to f. Now what is this new thing which we seem to not have shown, but it is something that you can just simply you can just simply see that it is true. It's not anything very complicated or big. It's simply an observation. Note that for any alpha belonging to F, alpha is itself a polynomial in X. Hence, and that is just simply another way of saying that f is contained in fx, or rather can be embedded in fx. So any field element itself can be regarded as a polynomial in x, a constant polynomial, what we normally call as a constant polynomial. So on alpha also you can apply tau star. If you do that, you get this. Hence, by the definition of tau star, alpha tau star is what? Now, being a constant polynomial, alpha really looks like just simply like this. If you want, you can say consider like this. So if you apply tau star on this, what will you have? What will be the tau star image of this? This, where of course these terms will not be there, so we will be left with alpha tau, which by our notation is nothing but alpha prime. So we can write like this: alpha tau star is by definition alpha tau, which is alpha prime, and that is what we have just mentioned here. Okay, now next we are going to again use another simple notation, just like how we decided to write alpha prime in place of alpha tau. We are now going to write we are going to use a similar notation for writing the tau star image of fx, because now you see previously we had an isomorphism between f and f prime. Now we have shown that there is an isomorphism defined using this previous isomorphism between these two polynomial rings. So just like we had this simple notation, we can devise another simple notation which involves images of polynomials here under tau star. So in our on our journey towards that final result that we mentioned in the beginning of this video, this is one result. So like that there are others also. If fx belongs to the first polynomial, we shall write the image of fx under tau star as f prime t. keep in mind that because tau star takes us from this polynomial ring to another polynomial ring where the indeterminate is t, this entire thing is after all a polynomial in t over the field f prime. So that's why we are writing t here, and the fact that the field is f prime is expressed by writing a prime here, but this notation looks extremely confusing simply because of the fact that it looks like the derivative of the function f at t. However, you forget about derivatives because we are doing algebra, where we are considering, if one wants, one can consider the derivative of a polynomial over any field of a polynomial at least, which does not need you to consider limits or anything, but we are doing algebra, so forget about analysis or calculus for now. Okay, this now just simply means this thing. So now what does this lemma say? This lemma tells us immediately, in the language of Herstein, implies that factorizations of fx in fx correspond to factorizations of f prime t, that is image of fx in that other polynomial ring, simply because these two polynomial rings are isomorphic, and not just that, the underlying fields are also isomorphic. So in a sense, actually we are considering a single field and a single polynomial ring over that field. Result in like polynomial factorizations, like factorizations, similar factorizations of f prime t in f prime t. In particular, f of x in fx is irreducible in fx if and only if its image under tau star, that is f prime t, is irreducible in f prime t. All these statements are actually trivial because the rings and the fields, the polynomial rings and the fields involved are isomorphic to each other. But the question now arises, it may have arisen in your mind, okay, so we wanted to compare isomorphic fields, which is how we started this discussion. We started the discussion by considering two fields f and f prime which are isomorphic. There is an isomorphism from tau from f to f prime. But now why are we transitioning from that situation to polynomial rings? Because after all we need fields, no? So why polynomial rings? That is because that is how we in fact created extensions of a field in which a polynomial will have one root. You see, what we did is this now. If say p of x is, recall what we did previously, f is a field, say p of x is an irreducible polynomial in fx. Then we consider the principal ideal in fx generated by p of x, that is this, and we consider the quotient ring of this polynomial ring by that ideal. This we showed actually becomes a field, which is in fact, it turns out to be an extension of the original field f, in which this p of x has a root. So in achieving these extensions, actually we went through, we did not just simply obtained an extension of f right away. We did this via polynomial rings in this manner. So that's why after having this isomorphism between fields, the next stage is to go to the larger system, the polynomial ring, and then make the polynomial ring collapse in this manner by taking an appropriate quotient, and that creates the extension field. So that's why we are going like this. First we have f, then we are considering the polynomial ring fx, then next we are going to consider these quotients of the polynomial rings, which will turn out to be fields. So that's why the author writes like this. However, at the moment we are not particularly interested in polynomial rings. But rather on in extensions of f. Of our original field f. However, what does Herstein write? Let us recall whatever I just said right now. Let us recall that in the proof of theorem 512 we employed quotient rings of polynomial rings to obtain suitable extensions of f. And that is why we are doing all these things. In the proof of theorem 5.2, is it 5? No, not 5.2.1, 5.1.2. The second section of this chapter is, I believe it was that thing, no? Transcendence of the irrational number e. That is entirely different. So it is the first section itself. We employed quotient rings of polynomial rings to get a suitable extension of our field F. In consequence, it will be natural for us to now take the next step. We have already taken one step from tau, we have gone to tau star, okay, which is an isomorphism between polynomial rings. So now we take the next step. We are going to now seek a function tau star star, double star, which will be an isomorphism between quotient rings of polynomial rings. Investigate the relationship between this quotient ring and this other quotient ring f prime t by this principal ideal f prime t, where I am not writing, you already know what these things are. This thing is the principal ideal generated by fx, and that principal ideal is an ideal of this polynomial ring fx, and this one f prime t, this is the principal ideal generated by that polynomial in this polynomial ring f prime t, and in this direction this is that next lemma. The nature of the proof of theorem 512 forces us to take this path. Had we directly got the extension E without mentioning polynomial rings or anything, we would not have, of course, proceeded in this way. So this is the next lemma, 534. It is mentioned in the form, lemma 533 also mentions, the statement of lemma 533 does not say something like this, that there exists an isomorphism tau star from f of x to f prime of t, such that if you apply tau star on any element alpha in f, you get alpha prime. If you want, you can state the statement like that also, like an existence statement, and then show that our particular tau star in fact qualifies to be such a function, such an isomorphism. But because we started with tau star, started by defining tau star, and then we showed that tau star is one such isomorphism, so we just simply wrote tau star defines an isomorphism from fx onto this and that. Here, however, we write the statement first and then we will prove it. So we write like this. there is an isomorphism tau double star of this onto such that here also for every alpha belonging to F, alpha tau double star is just like what we had before, alpha prime. And also additionally this happens now. I'm not going to prove it in this video. We will prove this one and we will see some other subsequent results in the next video. But at least let us see what this thing means. What this first part means is, of course, it's understandable. Tau double star is an isomorphism of this quotient ring onto this quotient ring. But what about this alpha tau star star? You see, you have these two transitions, right? You can move from this field into this larger system, polynomial ring over that field, and then you can consider something else, this quotient. Now in these two transitions can be really, I mean, here of course we can embed F into this ring, and in that sense you can in fact consider F itself to be a subset of Fx. Actually, strictly speaking, F is not a subset of Fx. The elements in F are field elements, whereas the elements in Fx are polynomials. But because we can identify field elements with constant polynomials, so that identification allows us to think of F as a subset of Fx. Now, can we still go one step further and identify still F as a subset of this? We can. And the identification, the specific identification we need in order to do that is this. You take a field element alpha, you identify that with this coset of the ideal, principal ideal generated by Fx. If you do that, you will see that you are getting a one-to-one homomorphism of the field F into this quotient ring, whose image has elements which look like this. So in that sense, in place of every alpha, you can think of this thing, and these particular type of cosets, they will behave like scalars. You can understand probably what I am trying to say at this stage. So that in that sense, we can in fact think of F to still be a subset of this somewhat quite complicated quotient ring of a polynomial ring. And that is why, because we can think of f as a subset of this, and tau double star, which we are saying is going to be an isomorphism from this polynomial ring into this from this quotient ring to this quotient ring. So we can find the image of any alpha in f, which now because of this identification can be regarded as an element here. We can find its image under tau double star, and what we are saying that image is going to be equal to alpha prime. But what is alpha prime? Alpha prime needs to be here. Strictly speaking, just like alpha is not actually here, but its shadow is here under this identification, alpha prime also has its shadow under a similar identification in this second quotient ring, and that identification also is just simply this. In place of alpha prime, you think of this coset of this ideal in this second polynomial, second quotient ring. So that is the real meaning of this. So that means that this equation you see here, alpha tau star star equal to alpha prime, really just means this. Okay, so that means we will have to, in the proof of this lemma, which we will do in the next video, we will have to first of all define this tau double star, and then we will have to show all the things that it's an isomorphism of this ring onto this ring, and also this we have to show, and next this also we have to show. Okay, so we will see these things and the other things that come after all these things. It is unlikely that we will be able to prove the actual final goal of this section that we were mentioning back then in the next video, but the video after that, there of course we will complete this section and then we can move on to the exercises. So I am ending things here for tonight. If you want to if you want to make some remarks on this, you can write in the comment section below, or you can mail me at my usual address. The link will be there in the description. Tomorrow we again have, in the last week we did Galilean's exercises. So tomorrow we are going to do exercises from Lee's algebra. So that being said, this is just it. I am wrapping things up. So see you tomorrow with Lee's algebra exercises. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.